This is the second presentation on multiplexing and demultiplexing. Here the emphasis will be on demultiplexing. And again, both multiplexers and demultiplexers are just an example of truth tables, so we will look at that. And the multiplexer, the job of the multiplexer was to select a source, and the job of the demultiplexer is to pick a destination. So there were a number of sources, and the multiplexer picked which source got through onto the shared channel, and then that shared channel is fed into the demultiplexer, and the demultiplexer is going to pick which destination the source information goes to. So let us discuss the nomenclature involved with demultiplexers, which are also known as DeMUXs. A demultiplexer will have one data input. It will have several outputs, and one of those outputs will be selected, and then there will be some select or addressing inputs to pick which output is the chosen one. Now, because we're working in binary and our addressing is binary, then the n, the number of outputs, is usually a power of 2. So we can either talk about a 1 to n demultiplexer, where we're saying there's one input going to n outputs, but another common nomenclature for demultiplexers is to tell you the number of address inputs. So you might talk about a 3 to 8 demultiplexer, where there are 3 addresses, and with those 3 addresses you can pick one of the 8 destinations. Just as the multiplexer is sort of pure combinatorial logic, just an example of a truth table, the same is true for the demultiplexer. The difference is that maybe the demultiplexer has many outputs, so it will be many truth tables, but each individual output is dependent only on the data input as well as the select input. So it's exactly the input that leads to the output. There's no memory. It's not sequential. You don't have to be in a certain state, you get a different answer. It's always dependent just on the select inputs and the data inputs. And so then, again, the DeMUX is just combinatorial logic, just a truth table. So here's the truth table for the 1 to 4 demultiplexer, or you might call it the 2 to 4 demultiplexer. If you're saying it's 1 to 4, you mean that there's one data input going to 4 possible outputs. And if you're calling it a 2 to 1, you're emphasizing the selects, the addresses. So you're saying there are 2 addresses, then help identify which of the 4 destinations is the chosen one. Okay, so here's the truth table. There are 2 selects, A and B, and 1 data input, D. And so there are 2 to the 3, there are 3 inputs, there are 2 to the 3 lines in the truth table, so 8 rows of the truth table, so they're all shown here. And there are 4 outputs labeled 0, 1, 2, and 3. So if A and B are used to pick one of the outputs as the chosen output, and then it gets the data, and then otherwise it gets a 0. So when A and B are 0, then the data, D, which might be 0 or 1, goes through output 0, and all the other outputs for output 0 are 0. Similarly, if A is 0 and B is 1 down there in the sort of 3rd and 4th rows, then the data gets through to output 1, and otherwise the data is 0. When A is 1 and B is 0, the data gets through to output 2, and when A is 1 and B is 1, the data 0 and 1 down there at the bottom get through to output 3, and all the other output 3s are 0. Now first, recall again that as a demultiplexer, it has 4 outputs. So look down and see that the gate version has 4 probes. There are 4 outputs that we are examining. There's no OR gate at the end, sort of combining those four things. They are four individual outputs. Then notice that each output is mostly zeros with a single one. That makes it a very easy to use the sum of product approach. There's a single one, we write the expression for that row. So let's look at that. O output 0 has a 1 in the second row. It's A is 0, B is 0, and D is 1. So that is A prime, B prime, and D. And so that's just a 3-input AND gate leading to that output. And similarly, output 1 has a single 1 as its output, and that is when A is 0, B is 1, and D is 1. So that is A prime, B, D. Output 2 has a 1 down in the row where A is 1, B is 0, and the D is 1. So that is A, B prime, D. And output 3 has a 1 in the very last row, which is A, B, D. A variation on a demultiplexer is a decoder. We take away the data input and just have the select inputs. And so then there are, in this example, 4 possible outputs, and it is the selected output will be high and the others will be low. So it's not data that gets through, it's just a pure selection process in a decoder. So here we see the truth table for a 2 to 4 decoder, meaning that there are 2 selects and they lead to 4 possible outcomes, only one of which will be selected. And so we have the inputs are the selects A and B, and then we have 4 outputs, and each output is chosen by the combination A-B. So when A is 0 and B is 0, we're choosing output 0. When A is 0 and B is 1, we're choosing output 1. When A is 1 and B is 0, we're choosing output 2. And when A is 1 and B is 1, we're picking output 3. So here is the 2 to 4 decoder built with gates. We have just 4 2-input ANDs with all the various combinations of A and B, and then each AND gate leads to one of the 4 outputs, output 0, output 1, output 2, output 3. So here we want to discuss the role of a decoder in RAM, random access memory. So a register is a unit of memory that holds a word. So it may hold 32 bits or 64 bits. An example of a register is the accumulator. It's the register used in conjunction with the arithmetic logic unit, the ALU. And you can sort of think of it, the ALU is where the math is done, and so the accumulator is sort of a scratch pad, a sort of a temporary holding area for little answers until you finally arrive at your final answer, which then you will want to store somewhere. Anyway. Memory, or RAM, or random access memory, on the other hand, is not just a single register, but a large collection of registers that hold lots of different things, data or instructions or what have you. And then, in order to function random access memory, we need to be able to pick one of the registers, one of the locations, and access it. That's what we mean by random access, sort of supply some address and then get the data that's being stored at that address. And so we have a set of registers, and then we also have a decoder, and then the job of the decoder that we saw is to pick one thing. And so in the case of RAM, what we are picking is one register from among the set of registers. So in RAM, first we have the memory address register. This is a simple single register that holds address and then presents that address to the decoder, so it serves as input to the decoder. Then the job of the decoder is to have one output selected and the rest deselected. And that output is fed to this bank of registers that is RAM. And so one of them is chosen, the one that we're sort of, the decoder is pointing to. So you feed an address into the decoder picks out the output with that address and leaves all the other ones deselected. And then that memory then can be worked with, either stuff put in or stuff taken out. It can be written to or read from using another register, the memory data register. So there's a single register on one side for addresses, a single register on the other side for data, and then there's a decoder that is fed an address, and then it selects out one of the registers among the bank of registers, and that's the one that interacts with the MDR. So that it will take data in from the MDR or to send data out to the MDR. Related to the idea of RAM, random access memory, is ROM, read-only memory. In random access memory, we supplied an address, and then we could access a register, some memory that was associated with that address, and we could write to it or read from it. With ROM, you do the same. You provide an address, and then you can access information at that address. But in the case of ROM, you can only read it. So the same input always yields the same output. So it is purely combinatorial as compared to RAM, which is sequential. That in RAM you remember what was written. You have some concept of a state which must be remembered. ROM is pure combinatorial. So it's really just a truth table. But we take the sort of opposite approach we do in a Carnot map, where we simplify it as much as possible. In ROM, we try to leave it generic so that almost any output is easily written when the time to do the writing in ROM, which only happens once, but occurs. So this picture here is trying to show the logic of ROM. So we have some address being fed into a decoder. And the job of a decoder is for one of the outputs to be selected and the rest to be deselected. So those are the horizontal lines coming out of the decoder, and one will be selected, the one associated with the input address. Then we have these vertical lines, and there are no nodes. Those horizontal lines and the vertical lines are not connected unless they're connected by the fuse, which is drawn as the sort of squiggly line. So there are fuses that might connect the horizontal lines and coming from the decoder and some vertical lines. And some of the fuses can be broken open. And so then in the process of writing ROM, we decide whether the fuses are connections or broken connections. And so that is a process that occurs only once, or in other versions of ROM sort of rarely. But again, so in ROM we have an address fed into a decoder, and then the decoder output is connected to a sort of orthogonal set of outputs through a set of fuses which may be connected or not connected. So we have the address fed into the decoder, and then you have the output of the decoder, which are these horizontal lines. Then the output of the decoder is attached to the output of the ROM, which are the vertical lines, through the fuses. And the fuses may be connecting or not connecting. They may be blown or not. And the normal voltage and current operation does not affect the fuses. You need sort of a higher voltage to sort of blow a fuse. And so then we put an address that selects out from the decoder one of the horizontal lines. Let's imagine it's the second one from the top. And then there is a corresponding value in the ROM that corresponds to the set of fuses for that horizontal line. So that horizontal line is connected to the first vertical line and not connected to the second vertical line. So the first vertical line may be then a 1 and the second a 0. And so this is a way to burn information into different addresses of ROM. So the writing of the values into the ROM occurs at a higher voltage. This is what sort of breaks the fuses or burns the ROM. And so we break some of the connections and don't break others. So we are writing information in sort of broken or not broken. This is sort of the binary of a fuse. And then under normal operations, the fuses don't change, so they will remain connected or not connected. So the information, once written, then becomes semi-permanent. And this is the basic idea of ROM. So it may not be a traditional fuse, but something fuse-like. This is sort of the logic of ROM.